Good afternoon, everybody. Welcome back to lecture number 39. Today we will have a very important lecture because it has lots of conceptual questions. So I just uploaded revision 2, where revision 2, last time we covered universal motor in the extra lecture 38.5. The recording will be uploaded soon, unless we have an objection. The single phase induction machine is what we are going to cover today. So in E360 we covered what? 3-phase wound rotor and 3-phase squirrel cage. You remember them. We also now know how to control them. And a very common question in the exam, can we? True or false? I can control squirrel cage using external resistor. False, you're right. You cannot. The external resistor is best for wound rotor because the squirrel cage is short-circuited cage. You cannot insert resistance to it. The other type of induction machine is the single phase. Here is mentioned 3, but in reality there is more 5 types depending on how you start them. We have capacitor start, split phase, capacitor run, capacitor start. I'll explain them today, but we will cover pretty much this area today. So in the previous lecture, the 38.5, what was the main argument? The main problem we have, if you have just one phase, one coil, it will not rotate, okay? It will not self-start. And if you spin it, it will be full of ripples. So they added an auxiliary winding to resemble a fake second phase. It's not a second phase, it's a fake second phase. So let me tell you a simple example to illustrate today's idea. You remember this AC circuit? What do we say? The voltage drop, or let's say the current in the resistor is in phase, صح? صح ولا لا؟ طيب. If I add either capacitor or inductor, is the I gonna be in phase with the voltage?
No.
No. Okay. Can I have some windings of the motor here, and I call them main, and I add another capacitor here? No. Main, and I add, and I have another auxiliary one here. Auxiliary ملحق. Can I split them? Would the current be in phase if they have the same value? Yes. If they have the same L, they will have the same value. But if I have L1 and L2, they have different values. صح ولا لا؟ ممكن هذا يكون at angle 2, this could be at angle 10. This could be at angle 40, this could be at angle 45. We don't know. But usually the difference between inductors is not that big. So if I add a fake capacitor here, what will be the phase shift here? It will be the phase shift due to the inductor, auxiliary, and due to the capacitor. So maybe I would have here 90 plus something, 90 because of capacitor 90. And here I have something. Not something, something else. But now I can run them using single phase source, but the flux comes from 2 different phase shifts. Get it?
Yes.
Get it why we call it fake 2-phase? In the 3-phase induction machine, you remember you have them like that. You connect phase A here, you connect phase B here, you connect phase C here, and then I don't know, you do whatever. So everyone gets a phase by itself. This is not the case. I only have one phase. But I play with the connections and the values of the windings to get different phase shifts. And that's why we call it auxiliary. Get it? Get it? This is very important to understand. If you understand this circuit, you will understand what I mean. We talked about the double rotating field theory, torque. The problem with, even if you do this connection, forget about the capacitor. The problem if you do two auxiliary windings that are spaced 90 degrees, you would still have an issue with zero starting torque. Yes, you will have two different curves, one for the main, one for the auxiliary. But this is still not good because it doesn't make sense every time I split. And what did we say the starting idea? The starting idea was, in the running condition, we can develop a torque with only the main winding. In the starting condition, you include the auxiliary one. And we said, at some point, we said at 75% of the speed, open this breaker. This is at 70 or 75? 75% of rated speed. We still didn't talk about the capacitor. نحن عشان نشرح الكونسبت, we have main winding, auxiliary winding. At 75% of the speed, open the brake. So this is only used to start. It doesn't use to operate. This gives you freedom to control only the main winding. But still, math is hard. Let's derive some math. Let's do some math. IA means I auxiliary. IM means I main. هذا وشو؟ main. هذا وشو؟ auxiliary. See هنا IA. هنا I. M. I think it's a small IA. Cosine whatever. Cosine whatever. So sub A مش معناتها phase A. معناتها auxiliary. The effective numbers of turns for main and auxiliary is N main and A. The windings are placed in quadrature. إيش معنى placed in quadrature? 90 degrees, correct. They are quadrature, عموديين. And you can see it here. You can see it يعني. If you have a two-pole machine, this is probably 90 degrees for two-pole machine. If you have more poles, it will be smaller. It will be 90 divided by 2, 45. If you have 6 poles, I don't know, small. If you have 8 poles, very small to achieve the quadrature. It's similar to achieving 120 degrees, but now they're spaced by 90. So start with the math. If you start with the math, you would get 4 main and auxiliary component. Last time we multiplied I with N. When in I, do the multiplication, and then you do 002. And whoever skipped 002 cannot do it because you apply the rules. Here, do you see why we have a square root of 2 instead of, this is not a peak, not max. This is RMS, okay? So that's why we have a square root of 2 here. And then you do the multiplication, derivation. Anybody knows where is there a half here? هل لازم يكون في half هنا؟ نص؟ No, right? No. Trigonometry ما فيها half. If you want to go from here to here, you divide by half. هل في أحد يعرف هل هو square root of 2 أو square root of 2 كانت 2 على جذر 2؟ Anybody knows the trigonometry? إيه بس هل قسمنا إيه ممكن هل يعني في 2 جذر 2؟ في عندي ال IM cosine هذه الجذر 2 جاي من فوق ما لها دخل. انا قصدي ليش ما قسم على 2؟ بالعاده يقسم على 2 في trigonometry. Whatever, check it. It doesn't matter. Divide by half or not. It's cosine of A plus cosine of B would equal to cosine A cosine B plus cosine. يعني هذه واحدة من التريجونومتري اللي تكون اللي تحت، مش اللي آخر مرة سويناها. Let's do the math. What do you see here? This is cosine omega t cosine theta. الكوساين ثيتا plus 90 خلاها ساين. cosine theta plus 90 خلاها ساين. This is math 02. Cosine omega t plus theta. هنا التريجونومتري هذا. أنا أقصد الهاف هذا. Yeah, it's not the same. Actually, it's not. It is irrelevant. Then what did he do? He splitted this part to be this thing. واضح? He splitted this part to be this thing. You don't have to know it. The derivation is out of the scope. So now how many components we have? 1, 2, 3. Okay? Using math 02. I really don't know these. I always refer to the tables. I think it's a crime. I think math 02 should give this in the formula sheet. Now, الفكرة إنه we have cosine omega t cosine phi, cosine omega t sine phi, sine omega t sine phi. We are doing now, I think we take this, we replace it with that, we plug it in here. So we get more terms. We get this term, we get this term from من الأحمر. We get also this term. Then you add and subtract. What will happen if you add and subtract? You get a mixture between the main والauxiliary times cosine. هنا كان كلها main لحال والauxiliary لحال. Now I'm having a difference between the main and the auxiliary. A difference between, this one is a function of the auxiliary. This one is an addition of the main and the auxiliary. This is a function of only the auxiliary. Okay? You can see it here. Terms with cosine omega t minus theta. When cosine omega t minus theta? This one. And sine omega t minus theta form forward rotating field. Terms with cosine omega t plus theta and sine omega t plus theta, they form backward rotating field. So I'm having backward, I'm having rotating. You don't have to know it, you don't have to write it in the formula sheet. It's just for understanding. Ultimately, what will happen if the theta is 90 degrees? Why? Because they are in quadrature. I would cancel out many of the terms. I would cancel out, for example, this term. هذا يصير cosine 0. هذا يصير cosine 90 صفر. Cosine 90 صفر. And I would be left alone with these two terms. 1 على جذر 2 زائد 1 على جذر 2 يعطيني 2 على جذر 2 اللي هو جذر 2. Okay? Then I have NMIM cosine of omega t minus theta. If NMIM equal to NIIA, يعني make everything equal, and what is sine theta? This will be 1. This will be 1. Add and multiply, it will be simplified to a rotating MMF. This is rotating MMF. And what is a key feature of this rotating MMF? It is self-started. خلاص هذا يدور من نفسه as a function of time. At time 0, it will be a value. At time, and as long as you have a rotating MMF, your starting torque is not 0. So this implies that T start greater than 0. So now we are here. Get it? واضح? This is very important. We simplify the math all the way by adding the main and auxiliary components if they are 90 degrees. Do math 02, not required. But what's required is you need to know the conditions. طبعا هو هذا كان example. Find the magnitude and the phase angle of the auxiliary winding current to produce a balanced two-phase system. So now we have actually a two-phase system coming from the single-phase supply. Any question about this part? Okay. So now, after I have the auxiliary, and now they are rotating, I face a problem. Is do I really want two-phase system all the time? Remember, it's a single-phase machine. There are many methods to keep the operation running, between start and run. The first part is the simple scheme that, similar to what I explained, you have the main, you have the auxiliary, and you add a switch at 75% of the rated speed closed. Okay? This diagram of, we call it split phase induction machine, is shown where auxiliary winding has higher resistance to reactance ratio. So now we are having higher resistance to reactance ratio. It means I'm making L smaller, because higher R over L, if I have a higher number, L has to be smaller. So I make the auxiliary winding, this L, smaller than this one. Well, where is the R? The R is the copper everywhere, okay? Then the main winding, so that two currents are out of phase. Already يصير عندهم out of phase. This is what I meant by having L1 and L2. So you have to create this phase shift. The higher RL ratio is usually obtained by using finer wire. For the auxiliary you use finer wire, أقل سمك من المين. في المين يصير we have bigger wire. Why do we have bigger wires for المين? What else?
Higher current.
Current rating. So, نحتاج resistance to be larger. You are right, that's correct. We can make R, that's correct. R is also larger. But the main reason is also to allow more currents. At the end, you play with R over L ratio. You also want to make sure the auxiliary winding is in the circuit only during the start. Then we have an auxiliary switch. We close it at 75%. But what is the problem with the auxiliary switch? Mechanical problem. What is a usual mechanical problem? If we don't use power electronics, what will happen? Switch may jam. Switch may jam. So this is the problem. So that's why it's old school. And the phasor diagrams are here. For your reference, you have IA and IM are not in phase. The resultant I, this is the supply I, this is the terminal I. You can see you get alpha degree between them. Now what is interesting is, if we ask you to draw you have the main and winding stage, then you only have main winding. This is very important. Please focus. I'll bring this curve in the test. If you don't have main and auxiliary winding, what is the starting torque if you have only one winding? Zero. If you don't have this 90 degree fine R over L, higher capacity solution, etc., you can have a higher starting torque up until you reach 75%. After the 75%, you suddenly drop the torque. You suddenly drop the torque because you're getting rid of your auxiliary winding. Does it make sense? If I get rid of my own windings, my torque will be smaller. It is effectively reducing your supply. Then I'm going to have my own curve speed using the main. So for running operation, this is run, this is start. Do you remember in many applications, run, start buttons? There is a run button, there is a start button. Have you ever seen a machine in real life where you have run, start? It's two different operations. You haven't seen?
Not yet.
When you join my favorite company, you will see. Okay? هذه الفكرة. This is very important. What is the issue here? I'm gonna have a sudden drop of torque. You have to make sure that your load is somewhere here. And that this peak torque is not needed. يعني if your load is here, the machine will crash. If the load is here, you're fine. Get it?
Exercise speed or
No. Torque over speed. This is torque over speed. CC is characteristics, I think. I used to say capability curve. I think it's characteristic. How do we start the torque? By messing with the ratio, R over L. What is the solution? Insert a resistance in the auxiliary winding. If you add a resistor here, what will happen? You increase R over L without having a bigger L. That's one solution. But what is the cost? The cost is heat, losses, etc. And remember, which one has wider cables?
main.
Main ولا auxiliary? Main. Okay, this is very important. المين أكثر من auxiliary. This curve is one of my favorite curves because it shows the sudden drop. So one question I might ask in the test for those who do not attend the class or watch the channel is if I put numbers, I tell you 280. Is this a safe operation? No. I put 130. Is it safe to switch to the run mode? So you have to make sure that this gap is not big enough. What is the other method? You add a capacitor. So you can add resistor, you can add capacitor. If you add a capacitor, what is the advantage? Your starting torque is higher. But what's the issue? The issue is you're still having a higher drop. Nothing is perfect. You have to choose one. You want high starting torque and you're going to suffer here. Because the problem with high starting torque is you already want a higher starting torque because you have a constant high torque application. But usually you're here. فيعني you have to design your curves. When you buy a machine, you always look at torque speed characteristics. If you buy it from manufacturer, not from third party seller. If you buy it from a manufacturer like ABB, GE, if they don't provide you the curve, you have to consider that. This is very important. And usually, the load is assigned by mechanical engineers. You ask the mechanical engineers about, can you tell me what are the torque, what is the torque, what is the speed? Now, the capacitor is an additional money, especially for big capacitor. This is a half horsepower. The capacitor is 300 micro. This is just a half horsepower. 300 micro is big. It's not a small capacitor and it's expensive. So high starting torque is the outstanding feature of capacitor start. This is capacitor start. Is it capacitor run? لا.
Doctor, if we are getting a higher torque, so why we don't just keep both winding for the whole?
If you keep both winding, then you use the capacitor run mode. You keep. But the issue with it is if you keep both windings, let's say you continue on this curve. You have a different curve. Maybe you have a different speed curve. You can't design it using two windings. But also why don't you use three-phase? Single phase are not efficient, but cheap. Single phase are not efficient, but cheap. If you use two winding, I would say it will cause issues with the control because all the control methods are either for single phase or three phase. The other issue is this capacitor in your vacuum cleaner. That is, if you keep it running, this capacitor might blow up. So it's about making your machine as simple as possible. So that's why we switch back to me. Also, the curve control might be harder. But I can tell you, it's better to get rid of the other winding.
دكتور كل ما كان الجاب أقل كان أفضل؟
لا الجاب هذه؟
إيه.
لا مش شرط أفضل. كل ما كان الجاب الطيحة من الجاب أعلى من اللود إذا أفضل. يعني whatever we settle here should be larger than the load. The problem is if you have a constant load, in this case you have a constant load maybe here, then this is not a good design. A good design should be here. Okay? So we have capacitor run. That's another type. So what do we have here? We have capacitor start. Capacitor run, it's your idea. Capacitor that's connected in series with the auxiliary winding is not cut after starting. Keep it. And left in the circuit all the time. This simplifies the construction and decreases the cost because of the centrifugal switch is not needed. We don't have this 75%. It may reduce the cost, but as I told you, the issue, if this capacitor is damaged, you're done. Your machine is not reliable. So you time your reliability to this capacitor. And this capacitor, if you keep it on all the time, it causes a problem. The power factor, torque, efficiency are also improved because now you have two phases. So the more phases is more efficient. 5-phase machine for space industry is more efficient. For military applications, they use 5-phase. The capacitor is compromised between the best starting and running value, and therefore starting torque is sacrificed. Yani you might not achieve very high starting torque because you have to make your capacitor smaller. If you make it big for operation, it's not good. So this is, I wouldn't use it much. But there is capacitor run mode. There is also capacitor 1 start, capacitor 2 start. And two different capacitor. واحد للstart, واحد للrun. Which is another solution. Again, two capacitors, one for starting, one for running. Optimum starting for running performance can be achieved. So the issue was also the running performance. The starting capacitor is larger in value and of the AC electrolytic type for, I think, more reliability. The running capacitor permanently connected and is of a smaller value and of paper oil type. Paper oil type, you can have it more. This is not beyond حفظ. It's beyond our cost. This is more high voltage application. The typical torque speed characteristics. Now we solve the issue of the dip. Our dip becomes a curve and then we have a slight dip. There we go. So I think this is the best combination. But of course it's very expensive and it doesn't make sense to buy it for a vacuum cleaner. So the issue here is the cost. It's your design. There is another type that's not much talked about, which what we call it shaded pole. Pole المظلم. Why we call it shaded pole? This is a salient pole. صح ولا لا? They are making here a hole and they put a shading coil على جزء من الpole. This is very interesting, you might explore it. So you shade maybe 10-20%, but you keep the others exposed. What will happen to the flux lines? They will be out of phase. So in the pole you shade some of it with coil. We call it the shading coil, but we still have the main coil. We connect this to the AC supply. And here we have the rotor. What is the necessary condition for shaded pole? It has to have a salient pole construction. A shaded band consisting of short-circuited copper tail. This is the shading coil. مظل الجزء من الpole. This is very important. The main single-phase winding is wound on the salient pole. The result is that the current induced in shading band causes the flux in the shaded portion to be lagging, to be different phase than the rest of the pole. It is similar to rotating field from the unshaded to the shaded, but the motor now has a starting torque. If you don't have the shaded pole, you start from zero. So your shaded pole just to give the motor a little kick of the start. However, this motor is not really used in real life much due to that it's salient pole, so you have a dedicated structure type. It's better to use the smooth air gap without salient poles for manufacturing reason. I told you before, maybe the stator is manufactured by company A. So there's a company that its only job is to produce a stator. If you tell them have salient pole and you have very few customers, then that motor, the shaded pole, will have a higher cost. So it's better to get a raw material from supplier that's focusing on one material. Okay? Similar to, this is actually business school. Which to me is not a school. Steady state analysis of single phase. Now, let's develop the equivalent circuit. The equivalent circuit is not that easy. But let's start with the rotor side. Do you remember in E360 or here, the circuit used to be like this, and then we have the windings, and then we have R2 over S. You remember this? تذكرون هذا الشيء? Now I'm taking this portion and I'm developing it from right to left. So how many circuits do we have? We have one for the forward, one for the backward. So one is a forward slip, one is backward slip. The forward slip equation is S, it's synchronous speed minus speed of the rotor over ns, this is well known. But for the forward, you apply a negative speed. If you apply a negative speed and do some math 0, 1, you will end up with 2 minus S. This is very important. So what is, if I give you a question, a single phase, what is the forward slip? It's the regular slip. What is the backward slip? It's 2 minus the regular slip. So I have 2 slips for single phase induction motor. So that's why controlling them is challenging. Controlling them is challenging. Here is the original circuit. Let's explore it. Do I have core losses? Do I have core model here? No, not needed. Because it's single phase. The idea that the motor, the 3-phase motor, is similar to a transformer comes from the fact that it has a constant rotating magnetic field, so it resembles a transformer. That's why we took the mathematical model of a transformer and we put it for an induction machine. But for the single phase machine, it's not a transformer, it's just winding. So we can even use the simplified circuit for induction machine. But the rotor is the complicated part. As you can see here, it has half of the resistances and inductors are forward, the other half is backward. For the forward, we divide it by S. For the backward, we divide it by 2 over S. But this circuit is difficult to analyze, so can I come up with a new circuit that everything is serious? Yes. And here is the equations how you transform them. We have Z forward, this is Z forward, this is Z backward. So Z forward, if you do the math, it's J.5 X max times this number over this number. And this is clearly a formula sheet friendly. We will solve an example next lecture. But what do you notice here? You notice this is a function of S, this is a function of 2 minus S. Here we have 2 minus S, here I have S. But this is the parallel combination of this and that. So if you don't want to know the formula, you can plug the numbers here and do the parallel combo. And you will get R plus JX. So I prefer to use the original circuits. Why I prefer to use the original circuits? Because if you use any simulation software and you want to compare the results, usually it uses the more accurate circuit, so you'll have better results. What is the power flow? What is the power? Okay, any question about the equivalent circuit? Keep in mind that the forward induced voltage is a function of the forward flux, the function of the backward, it's a function of the backward flux. Everything else is pretty much similar. You have R2, for example, resistance of the rotor referred to the stator, etc. Supply voltage, do we have line to line? We don't have line to line, please. In single phase induction machines, there is no line to line, because line to line is a feature of three phase system. So let's look at the power flow. Here is the power flow. We have air gap power forward, air gap power backward. And the equation for it is I1 square RF, I1 square RB. These air gap power, you can get them the air gap torque, which is using do you remember our issue? You remember the synchronous speed? You told me it's a typo.
ايوه يمكن انه هل نحط السليب سبيد ولا
Yes. So here we have the one that's before, or the one the converted, or the developed. This is the developed. So this is developed torque. This is at the gap, not after crossing the gap, not at the shaft.
electrical.
That's the electrical torque, correct. Okay? That is the electrical torque. واضح? So the resultant torque is forward minus backward. You have to subtract them because they are opposing each other. It's very important. This is challenging. Controlling it is going to be a disaster, but we're not going to control it. We're just analyzing it. So if you use the equation, it's a function of the two resistors, RF minus RB. This is RF, this is RB. Okay? This is RF, this is RB. So it's again a function of the slip. So the mechanical power developed now is a function of omega m. So you use 1, you multiply it by 1 minus s. It's the same as synchronous speed. It's this torque times synchronous speed, but now you multiply by 1 minus s. Why you multiply by 1 minus s? Because that's the formula. PG equal P converted. No, P converted is PG times 1 minus s. You remember this, 1 minus s is the efficiency. Okay, وين هو رجع؟ خلصتوا؟ Sam, Saeed, or whoever comes late, put L. Go back. And this side too, put L. Okay? Don't worry, I'm not going to take points from that. It's just to keep track. To make us look good in front of the department. Okay? Do you remember this equation? 1 minus S, RF minus RB. This one is similar to this one, except here we're subtracting the two air gap powers. One is forward, one is backward. As a matter of fact, this equation should be used, and always you should deal the two slips separately. So what's the output power? Is mechanical power minus rotational losses, minus friction, minus everything else. Okay? Whoever comes late, please put late. I'm not going to take a point, just for formality. The rotor copper loss produced by the forward field is, give me 2 minutes, is SPGF, and the reverse is what? 2 minus S. So this is the rotor copper losses. So it's also a function of the slip. Do you remember the copper loss is SPG. Do you remember that? So this is a similar one. You apply it forward and backward. And then you add both of them to add all the rotor copper losses. So the total air gap power is actually this one. The gap power is the sum of the forward and the backward. The mechanical power is calculated as the difference between. So air gap power هو الاديشن والmechanical power is the subtraction. Mechanical power is the subtraction. Keep these formulas in place, okay? Finally, what's your input power? It's forward plus backward plus copper losses, which is the supply. This is your input power. What is your power factor? Is cosine, omega, everything related to the supply. So basically, the input power or power factor of the input power can be calculated directly from the supply. And then your efficiency should be what? P output over P input. What is your P output? Is P mechanical minus P rotational. What's P mechanical? It's this thing. Rotational is given in the problem. Clear? So your key, we will solve inshallah this very long example in the next lecture. It's probably one of the longest examples in this course for single phase induction machines. Any question? Okay, sorry for the delay that happened earlier.